Hi everyone, welcome back to a new video. In this video we're going to talk about nucleophilic acyl substitution, and we're going to focus on acid chloride substitution. So first thing with nucleophilic acyl substitution, it's important to first off locate your nucleophile and your electrophile, and then it's important to also locate your leaving group. So let's start with the nucleophile. So in this case, we know that nucleophile are electron rich. And in this case, the lone pair on this oxygen is going to act like the nucleophile. So this is going to be our nucleophile. And we note that a carbon in a carbonyl group is electron deficient because of the electronegativity of this oxygen here that attracts the electron. So we can imagine that the electrons are much closer to this oxygen that leaves this carbon with a formal positive charge. So in this case, it makes this carbon a good electrophile. Furthermore, because of the chlorine ion here, the chloride or the chloride that is attached to the carbon, not the ion but the chloride, this is also electronegative. It attracts the electron. It takes the electron away from this carbon, and it cannot do any resonance. So this also increases the formal charge, or the partial positive charge, on this carbon, making it even more appealing or attracted to be attacked by a nucleophile. So we would then, in a mechanism, have this nucleophile attack this carbon, making this pi bond here roll up, give a negative charge. So here we would obtain a tetrahedral intermediate with positive charge on this oxygen and a negative charge on this oxygen here because of the roll up. Now, you might wonder why we have this pyridine here that doesn't have no H yet. Sorry about that. So this pyridine is used to deprotonate, so we do not obtain a leaving group or a leaving group with an HCl. So the leaving group of an acid chloride in this case would be the chloride that will leave and form a chlorine anion. And because a chloride anion is a weak base, it is then a very good leaving group. So it is eager to leave and be substituted. So this is going to be used to not only get a chloride anion instead of a HCl, right? So here, this pyridine with its lone pair is going to attack this hydrogen, and this bond here is going to roll up on this oxygen, making this pyridine and giving this oxygen here its neutral charge. There. Now that we have this, the last step we need to do is to have the chloride leave and reform the carbonyl group. Which gives us a acid chloride that was substituted into a carboxylic acid product, and we then have this chloride anion and this pyridine, which I forgot to mark this nitrogen here as positively charged. So here's the stepwise mechanism of an acid chloride acyl substitution, nucleophilic substitution. One thing that's important to remember is to locate not only your nucleophile and your electrophile, but also your leaving group in an acid chloride, because the chloride anion is going to be your leaving group. It shows you that it is ready to leave. Thus, any nucleophile is going to first attack the carbon, because the carbon here is very electron deficient, and this chloride ion or this chloride atom is ready to leave. So I hope this helped. Thank you for watching. If you guys have any questions, just leave them in the comment. Thank you.